Hello, everyone. I wanted to make a quick video to help you with a couple of things in section 4.3. So I wanted to go through this one example. I was able to do this example with one of my classes, but not with the other. And even in the one that, if we did this example in your class, I did get some questions on how to solve this. So I thought it would be helpful to have everyone go through this one. So I want to go through the mean value theorem start to finish with this example. So here we go. So in order to know whether we can apply the mean value theorem, we have two check boxes. So the first thing that we have to do is check our boxes. First box is my function, this one is called M, continuous on the closed interval from 7 to 13. To see if something is continuous, we're going to apply our domain rules. We have domain rules for logs, roots, and fractions. Only the log rule applies to this problem. So we're going to apply the log rule. And the log rule says that the stuff inside my logarithm, here that's x minus 6, needs to be strictly greater than 0. So as long as x minus 6 is greater than 0, I'm continuous. And so now I'm going to move that 6 to the other side. So I'm going to have that x has to be greater than 6. As long as x is greater than 6, I'm continuous. And notice everywhere in my closed interval from 7 to 13, everything in there is bigger than 6. So I'm just going to say everything in 7 to 13 is bigger than 6. So I'm continuous. Check. Okay, so we've used our domain rules to check that we are continuous on the closed interval. The next box that we have to check is my function M differentiable on the open interval from 7 to 13. That's the next box that we have to check. In order to tell if we're differentiable, I need to take the derivative and then see where that exists. So let's take the derivative. How do you take the derivative of the natural log of some stuff? Yeah, it's a chain rule, so you can do your inside and your outside. Or if you remember from logarithmic differentiation, there we go. The derivative of ln of some stuff is 1 over your stuff, which here is x minus 6, times the derivative of your stuff. The derivative of x minus 6 is just 1. So that means that my derivative is 1 over x minus 6. So that's what my derivative looks like. And the question is, where is this thing differentiable? For what values of x can I plug in an x value and get a slope out of this? And the answer is, well, as long as the bottom's not 0, as long as I don't divide by 0, I'm going to get an answer out of this. We're basically applying our domain rules to our derivative. That's essentially how we're going to do this. And so we need to apply the fraction rule here. And the fraction rule says that the bottom can't be equal to 0. So this says that x can't be 6. So I'm going to be differentiable as long as x is not 6. And since 6 is not in my open interval from 7 to 13, I'm differentiable here. Check. Yeah, so we're differentiable as long as x isn't 6, and nowhere in our interval is x 6, so we are good. So now we've checked our two boxes, so we know that the mean value theorem applies. Okay, and so now that the mean value theorem applies, it guarantees us at least one solution where the derivative at a single point is the same as the average rate of change between my endpoints. So we first have to find the slope of this secant line, the average rate of change between our endpoints, and then we are going to figure out where the instantaneous rate of change is the same value. Okay, so f of b, right? So our a and our b come from our interval here. So b is 13 and a is 7. F of b, I'm just going to plug b, which is 13, into my function. So that's going to be the natural log of 13 minus 6, which is 7, minus f of a. I'm going to take my a value of 7 and plug it into my function, which is going to be the natural log of 7 minus 6, which is 1, all over b, which is 13, minus a, which is 7. And now we can subtract these. On the top, there's a couple ways to look at this. The natural log of 1, this is kind of a known number. Doesn't matter what your base is, the log of 1 is always 0 because anything to the 0 power is 1. So this is just 0. So essentially on the top, I have the ln of 7 left. Or if you want to think about condensing on top, because we're subtracting 2 logs, you end up dividing inside 1 log. So when I combine these into a single log, I get the natural log of 7 divided by 1, and 7 over 1 just simplifies to 7. So however your brain likes that, whatever you see and makes sense to you, go with it. And then 13 minus 7 is 6 on the bottom. Okay, so this is my average rate of change. That's the slope of the secant line between my endpoints. And the mean value theorem guarantees that I have a place on my derivative where the instantaneous rate of change is the same as this. So I'm going to set my derivative, which we found up here was 1 over x minus 6, equal to this value that we just found, the ln of 7 over 6. And now I have to solve this for x over here. Now, this can be a challenging thing to do. You can either cross multiply if that's in your repertoire. I don't like to cross multiply because I think it can get confusing between that and regular fraction multiplication. So to solve this, I like to multiply both sides by both denominators. So I'm going to multiply both sides by 6 to clear this fraction on the right. And I also want to clear the fraction here on the left. So I'm also going to multiply both sides of my equation by x minus 6 so that I clear this fraction. And so when I do that, on the left, I have 6 times 1, which is just 6 left. On the right-hand side here, I have the natural log of 7 times x minus 6. And now, again, I'm still trying to solve for x. Now here, if you wanted to, you could distribute that ln of 7. But to be honest with you, the ln of 7 is just a number, and it kind of freaks people out because it's not the prettiest number. So I just want to get rid of it right now and just kind of cut it off at the pass so that I don't have to deal with it anymore. So if I divide both sides by the natural log of 7 here to get rid of that, I end up with 6 over the natural log of 7 over here, and then I have x minus 6 left on the other side. So I just divided both sides by that natural log of 7 to get rid of it. And now I want to solve for this x, so I'm going to add 6 to both sides. So if I add that 6 to both sides, what I have is, sorry, I'm running out of space. I'm going to come down here. I have 6 over the ln of 7 plus 6 is equal to x. This is my exact value of x. That's my c value, the number between a and b, between 7 and 13, where the slope, the instantaneous slope, is equal to ln of 7 over 6, which is my average rate of change between my endpoints. And if you're like, ooh, that doesn't look like it's between 7 and 13, if you plug this into your calculator, you'll find that it's 9 point something. And you will find that it is, in fact, between 7 and 13. Okay, so that is the mean value theorem start to finish. Check your boxes, find your average rate of change, and then set your derivative equal to that average rate of change and fight through the algebra to solve it out. All right. And then the last thing in this section we didn't get to, it's called Rolle's theorem. And honestly, Rolle's theorem is just a restatement of the mean value theorem with one very specific case. So really, if any time that it says to apply Rolle's theorem, you're really just applying the mean value theorem. So even if you apply the mean value theorem the way that we've always done, it's going to work out exactly the same, I promise. But it's a very special case which can just kind of, it streamlines a little bit, but not a ton. So here we go. Rolle's theorem says that if our function f is a continuous function on a closed interval from a to b, and differentiable, I didn't spell that quite right, but that's okay, differentiable on the open interval. And that should sound very familiar. This is the same opening statement as the mean value theorem. We need a continuous function on the closed interval and a differentiable function on the open interval. Now here's where we depart a little bit. If f of a is equal to f of b, we now have an extra statement that we have to kind of check and an extra hoop that we have to jump through. If the y values at our endpoints are equal, then Rolle's theorem says there exists at least one x value. I'm going to call it x equals c. And again, that x value is going to be in the open interval from a to b. That x value is going to be between a and b, such that, so I'm going to have at least one x value such that f prime of c equals 0. This is basically the mean value theorem with the specific case that the average rate of change between your endpoints is 0. So let's kind of think about this. If f of a and f of b are the same, then f of b minus f of a over b minus a, right? If these guys are equal, my average rate of change is going to be 0 over whatever b minus a is. 0 divided by any number is 0. It's basically the case where the average rate of change between your endpoints is 0. And it should kind of make sense because if this is your a value, here's your b value. If these have the same y value, then assuming that my function goes up from a, at some point I'm going to have to turn around and come back to b. And if we have to be continuous, it's going to be a nice smooth turn, which means there's got to be a place up here that has a horizontal tangent line. And so that also kind of just makes sense. So it's a very specific case of the mean value theorem where the slope of your secant line is 0. And that's going to happen when f of b and f of a are the same. Okay. So with Rolle's theorem, it's going to be just like the mean value theorem, but we've got one more box to check. The first box that we have to check is our function continuous on the closed interval. The second box that we have to check is our function differentiable on the open interval. And then the third box that we have to check is f of a equal to f of b. Essentially, if we just check this box, that's saying, oh, the slope of my secant line is 0, therefore I can just set my derivative equal to 0 and rock through. So it makes the actual solving part a little bit easier, but we do have one more box to check before we can say that Rolle's theorem applies. Okay, so let's try this. I want to verify Rolle's theorem for this function on the interval from -2 to 2. Now, verifying it means, does it apply? So to figure out whether it applies or not, we have to check our boxes. So first box, just like with the mean value theorem, is my function f continuous, there we go, on the closed interval from -2 to 2? That's a good question. Is my function continuous from -2 to 2, including those endpoints? Well, my function is x to the fourth minus x squared. So to figure out if we're continuous, we apply our domain rules. We have domain rules for fractions, roots, and logs, but none of those things apply here. I don't have roots, I don't have logs, I don't have fractions, no domain rules apply. So my function is continuous everywhere, from -infinity to infinity. Thus, we're good from -2 to 2. Check. Right? Continuity, check domain rules. The second box that we have to check, here we go, is my function differentiable on the open interval from -2 to 2? Okay. So to figure out if this thing is differentiable, again, we have to find the derivative, and we're basically going to apply our domain rules to our derivative. We're going to say, where does this thing exist? So f prime of x, my derivative here, is going to be 4x to the third minus 2x to the first, and that's my derivative. Where does this thing, do I have any problems? Does this thing fail to exist anywhere? Do any domain rules apply? Yeah, no, I don't have roots, I don't have logs, I don't have fractions. This exists everywhere. From -infinity to infinity. Thus, we are differentiable on the open interval from -2 to 2. No problems anywhere. Awesome. Now, because this is Rolle's theorem specifically, this is the special case of the mean value theorem, I have one more box to check to be able to apply this, and that is, does the f of a equal the f of b? Well, I don't know. I'm going to have to plug these numbers in. So let's find f of a, which is going to be f of -2. So I'm going to plug -2 into my function. And again, f is my OG, so I'm going to plug it in here. So I'm going to have -2 to the fourth minus -2 squared. Whoa. And so I'm going to have -2 to the fourth is 16. That's a positive 16. Minus -2 squared is 4. 16 minus 4 is 12. And then I have to find f of b, which my b value here is right here, 2. And so if I take 2 and plug it into my OG function, I get 2 to the fourth minus 2 squared. And again, 2 to the fourth is 16. Minus 2 squared is 4. I get 12. Again, these are equal, so I can check that box. F of A is equal to F of B. I've checked all the boxes. Thus, Rolle's theorem applies. And if it says verify Rolle's theorem, it's just saying show that it exists. If we wanted to, we could find the places where the derivative is 0. Basically, because Rolle's theorem applies, it guarantees that we have at least one x value where the derivative is 0. We could find it if we wanted to. Here, it's not too bad. We're going to take our derivative, 4x to the third minus 2x, and set it equal to 0, and we'll just solve this out. We'll take out that 2x that's in both of these, and I'm going to have 2x squared minus 1, and that means either 2x equals 0 or 2x squared minus 1 is 0. So x equals 0, or 2x squared equals 1. And x squared is 1/2. And that means x is plus or minus the square root of 1/2. And we actually, I think if you plug this into your calculator, you will find that the square root of 1/2 is both positive and negatives are in here. So I actually have 3 places where my derivative is equal to 0 in this interval. So we're guaranteed at least one. Here we actually have 3 places: 0, positive square root of 1/2, and negative square root of 1/2. And again, just to verify that Rolle's theorem applies, you just have to check your boxes. But if you wanted to finish the theorem, this is how you would do it. Okay, so that was kind of extra. And now we're actually going to do this for another one. So again, for g of x equals x squared over 5x minus 8, I want to find all values in 2 to 8, that's my interval, such that f prime of c equals 0 by Rolle's theorem. So again, before we can apply Rolle's theorem, we have to make sure it applies. So we're going to check our boxes. Is g continuous on the closed interval from 2 to 8? I realize it gave us an open interval here, but we have to be continuous on the closed interval, which includes our endpoints. So we got to do the closed interval here and make sure we're good. Well, in order to see if we're continuous, we have to apply our domain rules. So we got a rule for roots, logs, and fractions. What applies? You got it. It's the fraction rule. Fraction rule says denominator, which is 5x minus 8, it can't be 0. And that means that 5x can't be equal to 8 if I divide both sides by 5. X can't be 8/5. Let's see, which is 1 3/5, so that's 1.6. For those of you in Camp Decimal. And so x can't be 1.6. 1.6 is where we have a discontinuity. Is that a problem? No, it's not a problem. 1.6 is not in my closed interval from 2 to 8. So we're still continuous on the closed interval from 2 to 8. My only problem is outside my interval, so I'm still continuous. All right. Second box that we have to check is my function g differentiable on the open interval from 2 to 8? Okay, how do we check this one? You got it. We got to find our derivative. And I'm not going to lie, finding the derivative here is not going to be super fun. How do you find the derivative of something that looks like this? Yes, it's a quotient rule. So you're going to call the top high and the bottom low, or the top F and the bottom G, and you are going to rock with your quotient rule. I like high and low, so here we go. Quotient rule for me is low, which is the bottom as is, 5x minus 8, times d high, the derivative of the top. The derivative of x squared is 2x, minus high, the top as is, which is x squared, times d low, the derivative of the bottom. The derivative of 5x minus 8 is 5, all over low, the bottom squared. 5x minus 8 squared. Okay, let's simplify this a little bit. I'm going to distribute this guy. We'll have 10x squared minus 16x. I'll multiply these guys, minus 5x squared, all over low, 5x minus 8 squared. Oh, and I have like terms here. So let's combine those. 10x squared minus 5x squared is 5x squared, minus 16x all over 5x minus 8 squared. Woo! Okay, that's my derivative. Okay, and in the process of doing that, I got myself a little lost. What are we trying to do here? Yeah, we're trying to figure out where this thing is differentiable, where this derivative exists. Well, this derivative is going to exist everywhere the bottom, which is 5x minus 8 squared, isn't 0. So as long as 5x minus 8 squared does not equal 0, we're differentiable. And again, I'm going to take this, so I'm going to take the square root of both sides. So that means I'm going to have 5x minus 8 can't be 0. And notice that's the same as I had up here. So again, I'm going to end up with the same thing that says x can't be 8/5. That's a 5, sorry. 8/5 or 1.6. Right, same thing that we got before. And again, 1.6 is still not in my open interval from 2 to 8. Thus, I'm differentiable on the open interval from 2 to 8. Basically, I want you to apply your rules and say, I have a problem at 1.6, but 1.6 is not in my interval, so I'm good. Okay, last thing that we have to check is f of a equal to f of b? And we're going to have to plug it in. A is 2 and b is 8. So here we go. F of a, I'm going to take 2 and plug it in. So I'm going to get 2 squared over 5 times 2 minus 8. And let's see, 2 squared is 4 over 10 minus 8. That's 4 over 2, which is 2. And f of b, b is 8, so I'm going to get 8 squared over 5 times 8 minus 8. 8 squared is 64 over 40 minus 8. That's 64 over 32, and that again is just 2. These are the same. All of these boxes, and that means that Rolle's theorem applies and guarantees me a place where my derivative is equal to 0. So now we can find it just by setting my derivative equal to 0. And so my g prime of x, which we found up here, was 5x squared minus 16x all over this 5x minus 8 squared. I want that to be equal to 0. This fraction is only going to be equal to 0. If you have a hard time seeing that, just start with setting this whole thing equal to 0 and multiply both sides by this denominator. And so when you multiply the left side by it, it basically cancels out and you get 5x squared minus 16x. When you multiply 0 by that denominator, it's still 0. So we're here to solve this out. I'm going to take out that x because that's the only thing that comes out of everything. And then we're going to have 5x minus 16 in here. And we can solve these out. Or 5x minus 16 is 0, which means 5x equals 16. And x is 16/5, which is, let's see, 3 1/5. So that's 3.2 for those of you in team decimal. And then, so we're guaranteed a 0, at least one in 2 to 8. Are both of these in there? No, this one's actually not in there. So x equals 0, this doesn't count as one of our guaranteed solutions. It's outside of our interval, but the 3.2, this one is in our interval. So this is the one that the mean value theorem guarantees us. Sometimes you get a bonus solution that's outside of your interval. That's okay, but you're guaranteed to have at least one that's inside your interval. All right, and that's Rolle's theorem. So it really is the mean value theorem. It's just that it's a very specific average rate of change. Yeah, I hope that helps with 4.3. Happy homeworking, and I will see you next time.